Hello, my friends, and welcome to Hafee Sleep, where we soothe the mind and explore the universe, one dreamy question at a time. Have you ever lain in bed, staring at the ceiling in the quiet of the night, and wondered about your place in it all? Maybe you're watching this from a bustling city where the lights drown out the stars, or from a quiet countryside where the Milky Way is still visible. Maybe it's the middle of the day for you, and you're just taking a moment to escape. Wherever you are, and whatever time it is, I'm so glad you're here. Tonight, we're embarking on a cosmic journey to answer one of the most profound questions we can ask. Is there a true center of the universe? We'll voyage from ancient campfires to the edges of space and time, unraveling a mystery that will completely reshape how you see the cosmos and your place within it. It's a story of incredible humility and even more incredible connection. So, get comfortable, relax, and let your mind drift among the stars. If this journey captures your imagination, please do subscribe to the channel and give this video a like. It truly helps us grow this quiet corner of the cosmos. And I'd love to know, where in the world are you watching from and what time is it for you right now? Let me know in the comments below. It's wonderful to feel our little community connected across the globe and the clock. Now close your eyes if you wish, and let's begin. Imagine for a moment that you're standing by a campfire on a perfectly dark, clear night. The flames crackle, casting a warm, flickering light on the faces of your friends. You look up. Above you, the sky is not just black. It's an immense, velvety canvas, dusted with an impossible number of stars. It feels vast, yes, but also intimate. It feels like you are right here, at the center of it all. The dome of the sky arcs perfectly over your head. Every star, every constellation seems to be arranged for your particular viewpoint. It's a feeling as old as humanity itself, that we are at the heart of creation. This feeling is our starting point, a deeply human intuition that we must gently, carefully, and wonderfully unravel. Now, let's take a journey. Not a journey on a spaceship, though we'll need one of those in our minds, but a journey of thought. We are going to ask a question that has tantalized philosophers, astronomers, and curious minds for millennia. Is there a true center of the universe? And if so, where is it? The answer, as we will discover, is far stranger and more magnificent than any campfire dream. It will challenge our very notion of what center even means. To find it, we must first understand not just where we are in space, but when we are in the grand story of the cosmos. We have to learn to read the light that has traveled for billions of years to reach our eyes. So, get comfortable. Let's begin our voyage by looking back, way back, to a time when our understanding of the center was simple and very, very wrong. So, let's linger here for a while, in this ancient world where the Earth was the unquestioned heart of everything. It's a powerful idea, and to truly understand why it held on for so long, we need to do more than just state it. We need to feel it, to see the universe through the eyes of a Babylonian priest, a Greek philosopher, or a medieval scholar. We need to forget, just for a moment, everything we know about space probes and telescopes and imagine relying solely on what our senses tell us. Because that's where this story begins. Not with complex math, but with the simple daily evidence of our own eyes. Every single day without fail, the sun rises in the east. It climbs steadily, majestically across the sky, and then descends in the west, plunging the world into darkness. There is no wobble, no hesitation. It is a perfect, reliable arc. At night, the stars perform a similar, though slower, dance. They appear as pinpricks of light, fixed in their patterns, the Great Bear, the Hunter, the Swan, and they rotate as one great sheet around a central point near the North Star. If you stay up all night with a keen eye, you might notice that the planets, the wanderers as the Greeks called them, move against this backdrop of fixed stars. But even they, in their meandering paths, seem to be journeying across our sky. The moon, too, changes its phase and position, but it never deviates from its apparent path around us. Now, what is the most straightforward explanation for all of this? If you are standing in a field and see a bird fly overhead, You don't think, the ground beneath me must be rotating and moving in a complex way to make that bird appear across the sky. No, you logically conclude the bird is moving and you are standing still. Scale that up to the cosmos. The most intuitive, the most obvious conclusion is that the Earth is a solid, stable, unmoving platform, and the celestial bodies are moving around us. This isn't a foolish idea. It's a brilliant piece of deduction based on the available evidence. It's a testament to the human mind's need to find order and pattern. And this model, this Earth-centered universe, provided an order that was deeply satisfying. The Greeks, particularly philosophers like Aristotle, took this simple observation and built a magnificent, logical, and beautiful cosmic architecture around it. They imagined the universe as a series of concentric, transparent spheres, nested inside one another like the layers of a cosmic onion. At the very center was the Earth, solid and immobile. The first sphere out from Earth carried the Moon. The next sphere carried Mercury, then Venus, then the Sun, Mars, Jupiter, and Saturn. Beyond Saturn was the sphere of the fixed stars, and beyond that, a final, prime mover sphere that set the whole magnificent machinery in motion. These weren't just abstract ideas. They were thought to be made of a perfect fifth element called ether, a substance unchanging and divine, unlike the messy, imperfect elements of earth, air, fire, and water. This model wasn't just about mechanics, it was about meaning. It placed humanity in a cosmic hierarchy. The Earth at the center was the realm of change, decay, and imperfection. But as you moved outward, away from the corruptible center, you approached perfection. The heavens were perfect, unchanging, and divine. This philosophy resonated deeply with later thinkers, especially medieval Christian scholars. They saw in this model a reflection of God's plan. The Earth, the domain of mankind and sin, was at the lowly center, while the heavens, the abode of angels and God, were pure and perfect. It was a universe that made moral and theological sense. We were at the bottom, yes, but we were also at the focus. The entire universe, in a way, was structured around the human drama of sin and redemption. Now, a man named Claudius Ptolemy, working in the Great Library of Alexandria in the 2nd century AD, took these ideas and turned them into a precise mathematical system. His great work, the Almagest, was the masterpiece of geocentric cosmology. Ptolemy was a brilliant mathematician, and he faced a problem. The simple model of perfect spheres didn't quite match the observed motions of the planets perfectly. Most of the time, planets moved steadily eastward against the stars, but occasionally they would slow down, stop, and reverse course for a few weeks in a loop-de-loop motion called retrograde motion, before continuing on their way. This was a major flaw. How could the perfect heavens exhibit such erratic behavior? Ptolemy's solution was a work of genius, a complex but brilliant patch to keep the Earth safely at the center. He proposed that planets didn't move directly on their large spheres, called deferents. Instead, they moved on smaller circles called epicycles, whose centers were attached to the larger deferent. Imagine a cosmic spirograph. A planet goes around a small circle, the epicycle, and the center of that small circle itself travels around a large circle, the deferent, centered near the Earth. This combination of motions could beautifully explain retrograde motion. When the planet is on the part of its epicycle that carries it backwards relative to the deferent's motion, from our viewpoint on Earth, it appears to slow down, backtrack, and then move forward again. It was an illusion of perspective, but one created by real circular motions. To get the model to match the observed speeds and positions of the planets even more accurately, Ptolemy added other mathematical tricks. He placed the Earth slightly off-center from the deferent circles, a point called the equant. This meant the planets would appear to move at varying speeds along their paths, which they did. This system of deferents, epicycles, and equants was incredibly complex, but it worked. It could predict the positions of the planets with reasonable accuracy for its time. It was a testament to human ingenuity, the lengths we will go to preserve a cherished idea. For over 1,000 years, Ptolemy's model was the textbook of the universe. It was a complete, self-consistent system that explained the phenomena. It was, for all intents and purposes, the truth. But if you were a particularly careful observer, you might have started to feel a slight unease. The model worked, but it was becoming clunky. To account for finer and finer observations, astronomers had to add more and more epicycles upon epicycles. It was like a beautiful song that needed so many extra notes and harmonies to stay in tune that the original melody was getting lost. The universe, which was supposed to be a model of perfect simplicity and harmony, was being described by a mathematical contraption of breathtaking complexity. It was a system that saved the appearances, but it whispered a question: is this truly elegant? Is this how a divine creator would build a cosmos? This was the intellectual world for centuries, a world where the Earth's central position was as unquestioned as the ground beneath your feet. It was woven into the fabric of religion, philosophy, and science. To challenge it wasn't just to challenge a scientific theory, it was to challenge the entire worldview, the entire understanding of humanity's place in the grand scheme of things. The center was us. It was safe. It was comforting. It was home. But a few curious minds were about to look at the same sky, the same data, and ask a dangerous, revolutionary question. What if we are the ones moving? That creaking sound, the gentle groaning of a beautiful but overburdened idea, that's where we find ourselves now. We've left the comfortable, Earth-centered cosmos of Ptolemy, a universe that made perfect sense to our eyes and our ego. But science, as we said, has a habit of poking at comfortable ideas. It's driven by a beautiful restlessness, a nagging question that whispers in the dark, but what if? And in the 16th century, that whisper grew into a voice, a quiet but determined voice belonging to a Polish cleric and mathematician named Nicolaus Copernicus. To understand just how revolutionary his idea was, we really need to feel the weight of that Ptolemaic system. It wasn't just a theory, it was the operating system of reality for over a millennium. It was embedded in the liturgy of the church, the teachings of universities, the very language people used. The sun rising and setting wasn't a figure of speech, it was a literal description of the sun's daily journey around the earth. To suggest otherwise was more than just incorrect. It was, to many, a kind of madness, an affront to both reason and religion. The earth was stable, solid, unmoving. Everyone knew that. You could feel it beneath your feet. But Copernicus was a mathematician at heart, and mathematicians crave elegance. They look for simple, beautiful patterns underlying complex appearances. And to him, Ptolemy's system, for all its predictive power, was the opposite of elegant. It was a Rube Goldberg machine of the heavens, a convoluted contraption of circles within circles, off-centers and equants, all straining to make the celestial motions fit a premise that might be flawed. The most glaring problem, the one that kept astronomers up at night adding yet another tiny epicycle to their calculations, was that baffling retrograde motion. Let's spend a moment with this, because it's the key that unlocked the modern universe. Imagine you're tracking Mars night after night, carefully plotting its position against the fixed background of stars. For most of the year, it moves steadily eastward. But then, for a period of about 70 days, it does something bizarre. It slows to a halt, then begins to drift westward, tracing a narrow, looping path in the sky. After this loop, it stops again and resumes its eastward journey. In the Earth-centered model, this was a huge problem. The heavens were supposed to be perfect, and perfect motion, according to Aristotle, was circular and uniform. This backtracking was neither. It was an imperfection, a flaw in the celestial tapestry. Ptolemy's solution, the epicycle, was a brilliant workaround, but it was a workaround. It was like saying, the planet moves in a perfect circle, but that circle is itself attached to another perfect circle, and sometimes the combination makes it look like it's going backwards. It worked mathematically, but it lacked a certain grace. It was a patch, not a fundamental explanation. For Copernicus, this complexity was a clue. What if the complexity wasn't in the heavens, but in our point of view? What if the backtracking wasn't a real motion of Mars, but an illusion, a trick of perspective caused by our own moving platform. This was the brilliant, terrifying leap. What if the Earth itself was not the fixed stage but a player in the dance? What if, instead of the entire universe whirling around us every 24 hours, the Earth was spinning on its own axis once a day? And what if, instead of the Sun, planets and stars all orbiting us at different speeds, the Earth itself was orbiting the Sun once a year? The mental gymnastics required to accept this in the 1500s cannot be overstated. If the Earth spins, why aren't we flung off? Why don't birds get left behind in the sky? Why does a stone dropped from a tower land directly at its base if the Earth has moved underneath it? These were serious, valid objections based on the physics of the time. Copernicus didn't have all the answers. The concepts of inertia and gravity were still a century away. But what he did have was a mathematical model that was stunningly simpler. He placed the Sun, a brilliant, massive body, at the center. Then, in order of their orbits, he placed Mercury, Venus, Earth, with the Moon orbiting it, Mars, Jupiter, and Saturn. The daily motion of the stars, caused by the Earth spinning on its axis, the yearly motion of the Sun through the constellations, caused by the Earth orbiting the Sun, and that pesky retrograde motion of Mars? Ah, that was the masterstroke. Let's use that highway analogy again, because it's perfect. Imagine a circular racetrack. The Earth is in an inner lane, closer to the Sun, and Mars is in an outer lane, farther out. Because the inner lane is shorter, the Earth moves faster. Now, as both planets race around the Sun, there comes a point where the Earth on the inside starts to catch up to and overtake Mars. As we pull alongside and then pass it, our perspective from the moving Earth makes Mars appear to slow down, stop, and move backward against the distant background, just as a slower car you're passing appears to move backward relative to the distant horizon. Once we've passed it, Mars appears to resume its forward motion. The loop is not a real loop Mars makes. It's a parallax effect, a pure illusion created by our own motion. In one elegant stroke, the need for complicated epicycles vanished. The retrograde motion wasn't a problem to be solved, it was a natural consequence of the Earth's motion. It was a prediction of the model, not an exception to it. This was the Copernican revolution. But it's crucial to know that Copernicus was a cautious man. He knew his idea was explosive. His great work, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, was only published in 1543, the year of his death. Legend has it he was presented with the first printed copy on his deathbed. This might have been a strategic delay to avoid the inevitable controversy. And even in his book, he presented his model as a mathematical hypothesis, a convenient calculating tool, which was a common way to introduce radical ideas without directly challenging theological authority. He still clung to some ancient ideas, like perfect circular orbits, which meant his model wasn't actually more accurate than Ptolemy's for predicting positions, but the seed was planted. The central premise was out there. The Sun was the center. The idea needed more than math. It needed evidence. It needed a witness. And half a century later, it found one in Italy, a stubborn, brilliant man with a new toy, the telescope. Galileo Galilei didn't invent the telescope, but he was the first to point it at the heavens with a scientist's curious eye, and what he saw shattered the crystalline spheres of Aristotle forever. First, he looked at the moon. According to ancient doctrine, the moon was a perfect, smooth celestial sphere. But Galileo's telescope revealed a world. He saw mountains casting shadows, valleys, and craters. It was a landscape, rough and imperfect, not unlike the face of the earth, as he wrote. The heavens were not a realm of perfect, smooth ether. They contained worlds with geography. Then, in 1610, he turned his telescope to Jupiter. He saw 4 tiny stars arranged in a line near the planet. Night after night, he watched them. They moved, but they didn't wander away from Jupiter. They were orbiting it. This was a thunderclap. Here was a clear, visible counterexample to the idea that everything in the universe orbits the Earth. If 4 moons could happily circle Jupiter, then the Earth was not the mandatory center of all orbital motion. His most decisive blow to Ptolemy's model came when he observed Venus. In the Earth-centered system, Venus, as an inferior planet orbiting between the Earth and the Sun, should always appear relatively close to the Sun in the sky, and it should only show crescent phases like a tiny new moon, because we would never see the fully illuminated half of its face. But if Copernicus was right and Venus orbited the Sun, it should go through a complete set of phases just like our moon, from new to full and back again. When Galileo trained his telescope on Venus, that's exactly what he saw. It showed a full phase when it was on the far side of the Sun, and a crescent phase when it was on the near side. This was impossible in Ptolemy's model. The phases of Venus were the smoking gun, the direct observable proof that Venus orbited the Sun. Galileo, unlike the cautious Copernicus, was a fiery communicator. He published his findings in clear, accessible Italian, not just scholarly Latin, and he vigorously defended the Copernican system. This, of course, brought him into direct conflict with the church authorities, leading to his famous trial and forced recantation. But you can't unsee the truth. The evidence was now public. The Earth had been dethroned. The Sun was the center. So, for a glorious brief moment in the 17th century, it seemed the question was settled. We had found the center of the universe. It was our Sun. We had simply moved the seat of cosmic power from the third planet to the local star. It was still a comforting idea in a way. We may not be at the center, but our star was. Our solar system was the important one. We had traded geocentrism for heliocentrism. But this, as we will soon see, was merely a way station on a much longer, much more humbling journey. The universe was about to reveal that it was far, far larger and stranger than anyone had dared to imagine, and that the Sun, for all its brilliance, was a terribly ordinary citizen of the cosmos. The true revolution had only just begun. So, here we are. The Earth is spinning, orbiting a Sun that is the undeniable center of our local celestial neighborhood. A certain cosmic order has been restored, albeit with our home planet playing a supporting role. For scientists in the centuries following Galileo, this new heliocentric model was like a key that unlocked a new set of questions. With the Earth's motion understood, they could now turn their attention to the stars themselves. And what they saw when they really looked was both beautiful and puzzling. On a clear, dark night, far from the glow of cities, you can see it. A faint, milky, luminescent river arching across the sky. The ancient Greeks had a story for it, a spray of milk from the goddess Hera. They called it the Galaxius Kyklos, the Milky Circle. But what was it? Galileo, with his primitive telescope, had already taken a first peek. When he pointed his optic tube at this hazy band, it resolved into a vast, uncountable number of faint stars. It was not a celestial cloud, but a dense collection of suns, so far away that their individual lights blurred into a continuous glow. This was the first hint that the universe was much, much larger than just the solar system. But the true nature of this starry river was a mystery that would take centuries to solve. Imagine you're in a vast, dark forest. You can see the trees immediately around you, but the deeper parts of the forest are just a dense, impenetrable wall of darkness. The Milky Way was like that wall. We were inside it, but its structure was hidden from us. How big was this forest of stars? What shape was it? And where, within it, was our Sun? This is where an astronomer like William Herschel comes in. In the late 18th century, Herschel was a brilliant and meticulous observer. Along with his equally brilliant sister Caroline, he undertook a monumental task, to map the shape of the Milky Way. His method was ingenious, though based on an assumption we now know was flawed. He reasoned that if the Milky Way was a collection of stars, and if stars were roughly evenly distributed, then he could gauge the extent of the system in any direction by simply counting the stars he could see. It was a bit like trying to map the size and shape of a city by standing in one spot at night and counting streetlights. In directions where you see more streetlights, you might assume the city extends further. So, Herschel painstakingly pointed his telescope to different patches of the sky and counted. 1 star, 2 stars, 100, 1,000. He divided the sky into hundreds of regions and cataloged the stellar densities. The picture that emerged was dramatic. He found that the stars were densely packed along the band of the Milky Way, but thinned out dramatically above and below it. This led him to propose a model of the Milky Way as a grindstone-shaped or perhaps a long, flat slab-shaped collection of stars. It was a flattened disk, and our solar system, according to his star counts, appeared to be located right near the center of this disk. It was a comforting discovery. After the Copernican demotion, here was a promotion of sorts. We may not be at the center of the solar system, but we were at the center of the entire vast star system. Our sun was the capital city of the galactic empire. The universe might be vast, but we were still in the most important spot within our own island of stars. This idea of the Milky Way as an island universe, our entire cosmos, held sway for a long time. But the telescopes kept getting better, and as they did, astronomers began to notice faint, fuzzy patches in the sky, nebulae, from the Latin word for cloud. Some were irregular clouds of gas, like the Orion Nebula, which we now know are stellar nurseries, but others had a distinct, beautiful spiral shape. What were these spiral nebulae? The great debate, as it came to be known in the early 20th century, was fundamentally about the scale of the universe. On one side were those who believed these spirals were small, nearby gas clouds within our own Milky Way, perhaps other solar systems in the process of formation. On the other side were the visionaries who argued that these spirals were themselves island universes, distant galaxies comparable in size to our own Milky Way. The debate hinged on one critical, incredibly difficult question. Distance. How far away were these mysterious spirals? The key to solving this mystery was a special kind of star, a cosmic lighthouse known as a Cepheid variable. Certain stars, like the one Delta Cephei, were discovered to pulsate rhythmically, growing brighter and dimmer over a regular period. But the true breakthrough came from Henrietta Swan Leavitt, an astronomer at the Harvard College Observatory. Studying Cepheids in the Small Magellanic Cloud, a small satellite galaxy of the Milky Way, she made a profound discovery. There was a direct relationship between the pulsation period of a Cepheid variable and its intrinsic brightness. A Cepheid that took longer to pulse was inherently brighter than one that pulsed quickly. This was a revolution in cosmic measurement. Think of it like this. If you see a streetlight in the distance, you can't tell if it's a dim light that's close or a brilliant light that's far away. But if someone tells you that all streetlights of a certain type have the same true brightness, then you can calculate their distance by how dim they appear. Leavitt provided the standard bulb. By measuring the pulse period of a Cepheid, astronomers could know its true wattage. Then, by measuring how faint it appeared from Earth, they could calculate its distance with unprecedented accuracy. The yardstick for the universe had been discovered. Now enter Edwin Hubble. In the 1920s, using the most powerful telescope in the world at the time, the 100-inch Hooker telescope on Mount Wilson, which could peer deeper into space than ever before, Hubble pointed the giant instrument at the most prominent spiral nebula, Andromeda. He was searching for Cepheid variables, and he found one. Painstakingly, he measured its pulse period and then its apparent brightness. When he did the calculation, the result was breathtaking. The Cepheid, and therefore the Andromeda Nebula, was nearly 1 million light-years away. We now know it's 2.5 million. This distance was far, far beyond the then estimated boundaries of the Milky Way. In that single moment, the universe expanded in a way that dwarfed the Copernican revolution. The Andromeda Nebula was not a cloud within our galaxy. It was an entire galaxy itself, a colossal city of stars, separate from our own. The Milky Way was not the entire universe. It was one galaxy among many. Hubble soon found Cepheids in other spiral nebulae, revealing a cosmos filled with galaxies, each an island of billions of stars. The scale was now almost incomprehensible. Our solar system was a speck within a galaxy, and our galaxy was just one speck in a vast cosmic ocean. But the humbling wasn't over. As astronomers began to map our own Milky Way more accurately, thanks to new techniques for seeing through the interstellar dust that had obscured Herschel's view, they made another shocking discovery. Our sun is not at the center of the Milky Way galaxy, not even close. We are located in the galactic suburbs, about halfway out along one of the spiral arms, a place now called the Orion Cygnus Arm. The true center of our galaxy is a dense, bustling core of stars, thousands of light years away, surrounding a supermassive black hole. We live in a quiet residential neighborhood, far from the galactic downtown. So, let's take a deep breath and absorb this. We have been dethroned 3 times over. First, the Earth was removed from the center of the solar system. Then, the Sun was removed from the center of the galaxy. Finally, our galaxy was revealed to be just one ordinary member of a crowd of trillions. With each step, the universe has grown larger and our place in it has grown more ordinary. Is there any reason left to believe we are special? To believe there is a center at all? It was at this moment of profound humility, with the universe stretching out in all directions in a seemingly endless expanse of galaxies, that the most astonishing clue of all emerged. It didn't come from a new photograph or a bigger telescope. It came from listening carefully to the light from these distant galaxies and hearing a faint universal whisper that told a story nobody was expecting. The universe wasn't just big. It was moving, and it was telling us its deepest secret. So, we arrive at a crossroads. The universe is immeasurably vast, filled with galaxies, and we are in no special place. It's a static, almost majestic picture, a cosmic museum. But science was about to discover that this museum was not static at all. The walls were moving. The very floor was stretching. And the clue to this incredible motion came not just from looking, but from listening to the light of the stars. To understand how, we need to rewind a little and meet the man whose ideas made this discovery possible, Albert Einstein. In 1915, Einstein presented his theory of general relativity. It was a radical overhaul of our understanding of gravity. Since Newton, we'd thought of gravity as a force, an invisible string pulling the Earth towards the sun, the apple towards the ground. Einstein saw it differently. He proposed that what we perceive as gravity is actually a curvature in the very fabric of the universe. Think of space and time not as separate things, but as a single woven fabric, space-time. Now imagine this fabric as a taut, flexible rubber sheet. When you place a heavy object like a bowling ball, say the sun in the center, it creates a deep dip, a well in the sheet. Now take a marble, let's say the Earth, and set it rolling near the edge of this well. The marble won't travel in a straight line. It will curve, following the contour of the dent, orbiting around the bowling ball. It's not being pulled by a mysterious force. It's simply following the shortest path along a curved geometry. The Earth is following the curve in space-time created by the sun's mass. This was a breathtakingly beautiful idea. Gravity was geometry. Now, when Einstein applied his magnificent equations to the universe as a whole, he expected them to describe a stable, unchanging cosmos. This was the universal assumption at the time. The stars seemed fixed. The galaxies, though not yet known as such, seemed permanent. But his equations told a different story. They refused to describe a static universe. The solutions insisted that the universe must be either expanding or contracting. It could not be still. This made Einstein deeply uncomfortable. It was so contrary to all observation and intuition that he believed there must be a flaw in his theory. So he did something he would later call his greatest blunder. He introduced a fudge factor, a mathematical term he called the cosmological constant. This constant represented a kind of repulsive force, a subtle energy inherent in space itself that could perfectly balance the attractive force of gravity, propping the universe up and keeping it static. He forced his universe to stand still. While Einstein was wrestling with his equations on paper, astronomers were wrestling with the sky through their telescopes. A quiet, unassuming astronomer named Vesto Slipher was using a spectroscope. A spectroscope is a magical instrument. It takes light, say the faint collected light from a distant spiral nebula, and stretches it out into a rainbow spectrum, just like sunlight passing through a prism. But within this rainbow are dark lines like a barcode. These are absorption lines, the unique fingerprints of chemical elements. Every element, like hydrogen or helium, absorbs light at very specific wavelengths, leaving dark gaps in the spectrum. It's like a cosmic ID card.
Slipher began measuring the spectra of these spiral nebulae. He expected to see these fingerprint lines at their standard, laboratory-tested wavelengths. but he found something bizarre. For most of the nebulae, the lines were not where they were supposed to be. They were shifted towards the red end of the spectrum. This is a redshift. The only explanation Slipher and others had for this was the Doppler effect. You experience the Doppler effect every day with sound. When an ambulance speeds toward you, the sound waves from its siren are compressed, squashing together. This increases the frequency of the sound waves, and you hear a higher pitch. As the ambulance passes you and races away, the sound waves are stretched out. This decreases their frequency, and you hear a lower pitch. Light waves behave in exactly the same way. If a galaxy is moving toward us, its light waves are compressed, shifting the entire spectrum towards the blue end, a blue shift. If it's moving away, the light waves are stretched, shifting the spectrum toward red, a red shift. The shocking pattern Slipher found was that the vast majority of galaxies showed a red shift. They were all rushing away from us. It was as if we were at the center of a great cosmic exodus. This is where Edwin Hubble enters the story again. Hubble had the key piece of the puzzle that Slipher lacked: distance. Using Henrietta Leavitt's Sheafeed variable technique, Hubble could now measure how far away these redshifted galaxies were. He began the painstaking work of finding Sheafeeds in galaxy after galaxy, measuring their distances, and then comparing those distances to the redshifts Slipher and others had measured. What he found, published in 1929, was the most important cosmological discovery since Copernicus. There was a direct linear relationship. The farther away a galaxy was, the greater its redshift, and therefore, the faster it was receding from us. A galaxy twice as far away was moving twice as fast. A galaxy 10 times farther away was moving 10 times faster. This is Hubble's law. The implication was staggering. The universe was not static. It was expanding. It was growing in size. This discovery rendered Einstein's cosmological constant unnecessary. In fact, upon hearing of Hubble's results, Einstein reportedly said introducing the constant was his greatest mistake. The universe didn't need propping up. It was dynamically evolving. But this expansion leads to the most crucial point of our entire journey, the final answer to our question about a center. Our first instinct, upon hearing the universe is expanding, is to imagine a giant explosion. We picture all the galaxies as shrapnel flying outward from a central point. If that were true, then by tracing their paths backward, we could find that central point, the location of the cosmic bomb, and that would be the true center of the universe. But that is not what is happening. The expansion of the universe is not like an explosion in space. It is an expansion of space itself. This is the subtle but profound distinction that changes everything. Let's go back to our raisin cake analogy, because it's perfect. Imagine you are making a raisin cake. You have a lump of dough, and you mix raisins evenly throughout it. The raisins represent galaxies. The dough represents the fabric of space itself. Now you put the cake in the oven. As it bakes, it rises. The dough expands. What happens to the raisins? As the dough expands, every single raisin moves away from every other single raisin. From the perspective of any one raisin, all the other raisins are receding. The raisins farther away will appear to recede faster because there is more expanding dough between them. Now, here is the critical question. Where is the center of the expansion on the surface of the cake? Is there one raisin that is the center? No. Every raisin sees the same thing. The expansion is a property of the dough, not the raisins.
The universe is like the surface of that rising cake, but in 3 dimensions. The redshift we see from distant galaxies is not primarily because the galaxies are racing through space away from us. It's because the space between us and them is stretching. As a photon of light travels for millions of years across the cosmos, the space it is traveling through is slowly stretching. This stretching elongates the light wave, shifting it toward the red. The greater the distance the light has to travel, the more space has stretched during its journey and the greater the redshift. This is why redshift increases with distance. Therefore, if the universe is expanding like the surface of the raisin cake, then there is no center. Every point, every galaxy has an equal right to say, from my viewpoint, everything is moving away from me. There is no privileged location. The center is not a place in space. It's a moment in time. The center is the beginning. The center is the Big Bang. And the Big Bang didn't happen at a point in space. It happened everywhere at once. It was the moment when all of space, every point in the universe, was in an incredibly hot, dense state. So when we look out at the most distant galaxies, we are not looking out toward a distant center. We are looking back in time to a period when the entire universe, including the space right here where we are standing, was hot and dense. This is the final, beautiful, and humbling conclusion. We have journeyed from the center of the universe to a universe with no center at all. We are adrift on a cosmic raft that is itself part of the expanding ocean. There is no there. The center is everywhere and nowhere. It is a concept that belongs to the past, not to a location. And in understanding this, we finally see the true, magnificent nature of our home. So, is that the end of the story? In a way, yes. We've followed the trail of evidence from the Earth to the Sun to the galaxy and out into the cosmic expanse, and at every turn, the idea of a unique center has vanished like a mirage. But our minds are tricky things. We are pattern-seeking creatures wired for stories that have a beginning, a middle, and an end. And when we hear the phrase Big Bang, it conjures an image that feels very familiar, an explosion. And every explosion, from a firecracker to a supernova, has a center, a point of origin. So it's the most natural thing in the world to look at the expanding universe and think, aha, the Big Bang was the explosion, and everything is flying away from the blast site. That must be the center. This is the final and most stubborn intuition we have to gently unpack, because this intuition, while perfectly reasonable, is based on a misunderstanding of what the Big Bang actually was. Let's play that tape backwards, just as we said. We see galaxies flying apart, rewind, they get closer together, rewind further. The universe gets denser, hotter, keep rewinding. All the galaxies get so close that they merge into a seething hot soup of particles. Rewind still more. The universe becomes denser than a neutron star, hotter than the core of any star. If we rewind the clock all the way to time zero, we approach a state of infinite density and temperature, a singularity. It's tempting to picture this as a tiny, glittering pearl, a single point hanging in a void, which then exploded outwards into the emptiness around it. But this picture is wrong, and the key to understanding why is to remember what, exactly, is expanding. It's not the galaxies flying through space. It is space itself that is stretching. So when we rewind the expansion, we are not just moving galaxies closer together, we are shrinking the very space between them. Imagine the universe today is a vast, stretchy grid, like a gigantic sheet of graph paper where each square is a unit of space. Galaxies sit at the intersections of the grid lines. Now, as the universe expands, it's as if someone is stretching that graph paper in all directions. The grid lines move apart and the galaxies with them. Now, rewind. We are shrinking the graph paper. The grid lines get closer together. The galaxies get closer together. Now, rewind all the way. Shrink that graph paper down to the size of a postage stamp. What happens? Every single part of the graph paper is compressed. Every square is tiny. Every point on the grid is right next to every other point. There is no empty space around the postage stamp because the postage stamp is all the space there is. The entire universe, the entire grid, was compressed into that tiny volume. This is the crucial difference. The Big Bang was not an explosion into a pre-existing space. It was the explosive expansion of space itself. There was no outside, no empty void for the universe to expand into. The universe is not expanding in anything because it is everything, all of space. This is perhaps the hardest thing to visualize because our brains are used to things having an inside and an outside. But the concept of outside the universe may be meaningless. This is where the balloon analogy becomes so valuable even if it's not perfect. Let's really live on the surface of this balloon for a moment. Imagine you are a two-dimensional creature, perfectly flat, living on this two-dimensional surface. You have no concept of up or down. Your entire world is the surface. You can go forward, backward, left, right, but that's it. Now your universe, the balloon's surface, is populated by other flat creatures and flat galaxies. When the balloon is inflated, your universe expands. You see every other galaxy moving away from you. You, being a clever flat creature, might deduce that there was a beginning, a moment when the balloon started to inflate. You might call it the Big Bang, and then you might ask, where on this surface did the Big Bang happen? Which point is the center? But you would be asking the wrong question. The Big Bang didn't happen at a point on the surface. It happened to the entire surface at once. When the balloon was deflated, the entire surface was crinkled up into a tiny area. Every point on the surface was right on top of every other point. The moment of inflation, the Big Bang for your 2D world, happened everywhere on your universe simultaneously. The center of the balloon's expansion exists, but it's inside the balloon, in the third dimension, a dimension that you, as a flatlander, cannot perceive or even conceive of. That center is not part of your universe. Your universe is just the surface. Our three-dimensional universe is analogous to that two-dimensional surface. The Big Bang was the moment when all of our three-dimensional space began to expand. It happened everywhere at once. The spot where you are sitting right now was part of that initial, hot, dense state. So was the spot at the farthest galaxy we can see. So was every point in between. There is no location in our universe that is the site of the Big Bang because the Big Bang happened at every location. The center of our cosmic expansion would exist in a hypothetical fourth spatial dimension, which is not a part of our physical reality. We are trapped within our three-dimensional space, just as the flatlander is trapped on the two-dimensional surface. The ultimate proof of this is a faint signal that fills the entire universe, a cosmic fossil discovered by accident. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, annoying hiss in a giant microwave antenna. It was a constant, low-level noise that came from every direction in the sky, day and night, summer and winter. They cleaned out pigeon droppings from the antenna, they checked all the wiring, but the hiss remained. What they had stumbled upon was the cosmic microwave background radiation, or CMB. This is the afterglow of the Big Bang. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for atoms to form. Before this time, the universe was a hot, opaque plasma of particles and light, like a thick fog. But when atoms formed, the light could finally travel freely. That first flash of light has been traveling through the expanding universe ever since. But as the universe expanded, the light waves stretched, their energy dropping. What was once blazing visible light has now been stretched over 13.8 billion years into low-energy microwaves. This is the hiss that Penzias and Wilson detected. And here is the clincher. This background radiation is incredibly uniform. It comes to us with the same intensity from every direction in the sky, with only tiny, tiny variations. This means that 13.8 billion years ago, when that light was set free, the universe was almost exactly the same temperature everywhere. The region that would become the Milky Way was just as hot as the region that would become the Andromeda Galaxy, or a galaxy at the edge of the observable universe. This is powerful, direct evidence that the early universe was homogeneous, the same everywhere. And if the early universe was the same everywhere, then there is no special, unique center. The conditions of the Big Bang were present at every location. This idea that the universe is roughly the same in every place and in every direction on the largest scales is known as the cosmological principle. It's a fundamental assumption of modern cosmology, and so far, every observation supports it. The distribution of galaxies, the properties of the CMB, it all points to a universe that has no center and no edge. So, what does it mean to say, every point can consider itself the center of its own observable universe? The observable universe is the spherical region of space from which light has had time to reach us since the Big Bang. Because the speed of light is finite, we can only see a limited volume. We are, by definition, at the center of that sphere because we are the observers. But an alien astronomer on a planet in the Andromeda Galaxy has their own observable universe, a sphere centered on them. Their sphere contains galaxies that are too far away for us to see, and vice versa. Each observer has a unique, personal, cosmic horizon. In that limited sense, everyone is at the center of their own cosmic perspective. We have traveled an incredible distance from the campfire. We have moved from a universe that revolved around us to a universe that has no center at all. This can feel disorienting, even lonely. But it is also a vision of stunning democracy. There are no privileged frames of reference, no chosen people, no master galaxy. We are all equally part of this expanding, evolving cosmos, made of stardust, and gifted with the ability to look back in time and understand our own origins. The center is not a place you can visit. It is a story. It is the story of the beginning, a story that belongs to every particle, every star, every galaxy, and to us. And in that shared history, we find a connection to the whole of existence, a connection that is far more profound than simply occupying a special spot on a cosmic map. Good night. Have a deep, calm sleep.